Hello, everybody. Welcome to Group 5 Critical Design Review, sponsored by Ocean Insight. Our senior design project for this summer is Water Contaminant Analysis Raman Spectrometer, aka WARS. Our team working on this senior design project from left to right is George McDonald, Photonic Science and Engineering, Julia Smith Blanchard, Photonic Science and Engineering, Sebastian Johad, Computer Engineering, Gibran Khalil, Electrical Engineering, and Juan Vespro Diaz, Electrical Engineering. Like I said before, this is our project, a water analysis spectrometer. An overview of this is to make a device that will be able to recognize and detect contaminants in water. By analyzing the amount of light through the samples, this can be detected. The motivations that we have for creating this project is have a way to detect contaminated water in numerous places. Due to water being an essential resource on Earth, knowing which ones to drink is essential for not getting an illness. This is why we decided to create a water quality analyzer. Our project goals is to build a portable, cost-effective spectrometer that will focus on measuring different contaminants. With some of our constraints and sponsor needs, the device will be less expensive than models currently in the market. The size of the spectrometer will be portable but not too bulky. Also, the device will be simple and not overly designed. These goals will ensure that we are able to identify the presence of contaminants and be able to have a working product.
The core objective of this project is to produce a system that is capable of performing Raman spectroscopy. We will do this by developing a compact spectrometer that contains simple mounted optics, as well as by designing an illumination system. The advanced objective of this project is to develop a system that has a combination of a well plate reader as well as a detachable spectrometer in order to achieve a modular setup. By using a 785 nanometer wavelength laser, we can reduce fluorescence from the signal and be better able to identify our contaminant.
These are our engineering specifications and requirements. As you can see, there are three highlighted requirements that we will demonstrate in our demo. These requirements are an integration time of less than or equal to 10 seconds, the software being able to correctly process and compute Fizeau fringes in order to obtain Raman spectra, and the safety interlock engagement time being approximately instantaneous.
Our features are pretty simple. We want a computer application so that a technician could, put in their samples in the enclosure, run the program, and get their Raman graphs eventually at the end. The contamination detection is a feature of that basically, since you get to see the Raman graphs as they're getting spit out. You can look at them, and immediately for the trained eye that this machine is built for, they would be able to look at contaminants at an eye glance, basically. We want it to be moderate to have moderate speed, so for it to, go through the samples fairly quickly, given a 10-15 second time per sample. The X and Y table allows us to do the measurements of at least two samples at once. It just moves the table with the specific sample and allows us to measure them one after another. So our workload was split upon all of our members equally according to their majors and also their strengths. For example, we only have one computer engineer, Sebastian, and he was the one that did all the computer design, programming stuff, just make sure all the software works. Me and Juan are electrical engineering students, so we did all the electrical stuff like the physical safety systems and how they're powered, the precision motor, how to integrate it into the system, and also power supplies and thermal sensors and humidity sensors that we did. Our optical engineers were put on duty for all the optical design components, so things like laser lenses, gratings, and the heterodyne spectrometer, spatial heterodyne spectrometer, the modeling thereof, searching for their components, since that is their area of expertise. So we just split it off into the most, how do you say, appropriate roles.
This is a very brief introduction to Raman spectroscopy. It is important to understand that Raman is a very weak signal that is scattered when light causes molecules to vibrate. Some light remains at the same wavelength, and a tiny fraction shifts in wavelength. This is the Raman signal. Our spectrometer has very high throughput, making it attractive for Raman. When analyzing the intensity and wavelength of the material, one can uniquely identify that material. The SHS accepts input light, which reaches two separate gratings. Each grating diffracts the source light. Wave numbers or frequencies or colors are dispersed. The way light diffracts is described by the grating equation at the top. The Latrobe wavelength is the wavelength that produces a parallel wavefront, or in other words, where the first diffracted order is redirected back along the path of incidence. The grating must be tilted at the Latrobe angle to accomplish this. Resolving power dictates resolution, and spectral range describes the wavelengths that can be imaged upon the detector. Note that our spectrometer does not produce a conventional spectrum, rather it is encoded within Fizeau fringes that can be described by the fringe equation.
On the left shows the layout of the optical components, which includes the illumination system and the SHS. The illumination system includes the laser and the samples, and the SHS, which is the spectrometer, is the input of light and the detection of fringes on the CCD camera. So this is our optical system that we have designed for the use of being a Raman spectrometer. So on the left, you can see that it is a collimator that we have used to collimate the light from the fiber that is being transmitted in the laser. And then next, we use a beam splitter to split the beams onto the diffraction gratings. And then the diffraction gratings will be tilted at the Latrobe angle, which is the angle in which a wavelength is retroreflected back towards the same incident path, so all the light and the information can be collected. The face of the grating will then be imaged onto the detector, which will show a fringe image which looks like a barcode, which will then be transformed onto the camera that we have bought. Also, a focusing lens will be used to focus the fringes onto the detector, which has a small sensing size. The collimator lens is important to our design because it changes the diverging point source to a parallel beam. The reason we want this is to be able to capture all of the light and be ongoing into the beam splitter. I found a collimator package instead of designing one which would work for the limits of our spectrometer and has a tunable focal length.
Our lens design has an overall magnification of 1/4. The gratings are about 12 millimeters, and the vertical dimension of the detector is about 3 millimeters. The grating is about 75 millimeters from the first surface of this lens, while the image forms about 3.4 millimeters from the last surface. The total optical track length is about 99.6 millimeters. All three lenses will be housed within a lens tube barrel, along with an iris placed between lenses 2 and 3. This iris is the limiting stop of the system and will help improve the image quality.
This is an optical simulation and inverse transform result done in Zmax. When the fringes are imaged upon the detector, it will look like interference patterns. The image processing will be done in MATLAB. When this is done, the final result will show a spectrum and can be identified which contaminant was just analyzed.
So this is testing and verification by calibration. Basically, all you do is you select a light source that has distinct peaks. It's a line light source, but it has distinct peaks at specific wavelength locations. In our case, we chose mercury, and it has a high intensity peak at 546 nanometers, which will be helpful in selecting specific peaks for calibrating. But the basic idea is you would insert your light source, and then you would produce your fringes, go ahead and image process them, and while you're at it, go ahead and plot the peaks that you obtain from that Fourier transform against the number of pixels on the detector. Then you would pick 3 peaks, which is a statistical minimum, but then you would determine the position of the peak at the pixel as well as at the known wavelength in nanometers. So in this case, x-axis would be pixel position, and y-axis would be the known peak position in nanometers. And what you would obtain, if you can look at image B on the bottom, is what's called a calibration curve, and it's really just a line. So this is a linear calibration curve, and once you have all the pixel numbers from the equation that represents this line, you can plug them into X and then retrieve all of your wavelength values. which in this case is the Y value. And once you have all your Y values, you are now calibrated. So here are the results involving our measurements with mercury. The resolving power still remains to be about 6,000 because due to the input collimator optic that we have, the beam size is about 10 millimeters. When we used it with Krypton, the beam size was roughly the same. But here in this case, the beam size is still approximately 10 millimeters, which results in a resolving power of 6,000. And as a consequence, if you look on the slide, the next slide, we'll go into that, the resolution is about 0.4683 nanometers. Now the spectral range is just the number of pixels times the wavelength of the laser divided by twice the resolving power. And this results in a spectral range of about 86.184 nanometers, which is equivalent to about a Raman shift of 2620.58 inverse centimeters. So interestingly enough, we can pick up more Raman shifted frequencies compared to when we were using a 785 nanometer laser. So our known peaks when we measure mercury are 546, which corresponds in this case to about 265 pixels, 576 at 731, and 579 nanometers at the 829th pixel. When we have it set up like this, our R squared is about 0.9887, and the resulting linear calibration curve can be seen on the bottom right. I would like to note that peaks that shift by 800 centimeters inverse or lower are for some reason appearing weaker on our SHS. It may not be sensitive enough to pick them up at this stage, so the calibration is not perfect. But that being said, we are able to pick up specific wavelengths within our range, our spectral range, and the calibration that we have seen so far seems to be lining up, and we will show that on the next couple of slides. So looking at the bottom image, we can see that there are about two sets of peaks. You can see two on the left at 400 and roughly 700 inverse centimeters. Again, as previously mentioned, those peaks for some reason are not showing up on our plots. Again, I'd like to note that in our new setup, the 532 nanometer laser is going through our system, though our gratings are blazed at 780. We had to make a switch from infrared to 532 in order to work with the detector that we had and to allocate some space on our system such that we can pick up certain signals within our spectral range that shift. So the Raman shifts that we can pick up is the 1000, or in this case I believe it's 940 inverse centimeters, as well as the 1060 inverse centimeter peak. You can see the doublet on the bottom right of both plots. We have some arrows pointing from peak to peak, so we can pick up the 940 inverse centimeter peak pretty well, and the doublets are appearing pretty well as well. But also, if you take a look at on our plot, which is the top image, you can see at around 543 nanometers. There is a very tiny peak, but it's large enough to be seen. This could be one of the peaks that appear on the bottom plot, but it has an intensity, a very slight intensity of about 8.8. So now we're going to go ahead and compare the intensity levels based off of two different concentrations. The concentrations that we had prepared were a 1750 milligrams per milliliter sample as well as 550. For both of these images, the exposure time is set to 10 seconds, and for convenience, the scale of the images are set with a maximum count level of 160. Now, if you look at the top image on the left, you can see the fringes. Comparing the fringes on the top and the bottom, it is clear that the top fringes are brighter than the ones on the bottom. And you can notice for the same exposure time and different concentration levels that a 550 milligram per milliliter concentration does in fact bring back less of a signal. The intensity is less compared to the larger concentration sample.
This slide we will be focusing on sodium sulfate. So as you can see on the spectrum Raman shift versus intensity, we use that graph also by another group that did an SHS measurement on sodium sulfate. We use the orange line to reference what we got in our well plate reader when we measured sodium sulfate. So as you can see on the left, it has two distinct peaks, one around 1,000 and one around like 1,100, which is the doublet peak. So since our SHS is around 532 nanometers, our Raman shift will be looking at 1,000 and up because that's our range. 1,000 and down wouldn't really help us in our case. So as you can see in our SHS sodium sulfate measurement on the right, we have that distinct peak in wavelengths, not Raman shift. And then we have those two doublets which correspond with the sodium sulfate on the left. So with this slide, it shows two different comparisons of sodium sulfate, but one has a larger concentration, one has a smaller concentration. And they both have an exposure time of 10 seconds. So as you can see on the larger exposure time, the fringes are brighter, they are more distinct, and with the corresponding spectra, the counts are higher, and you can more visibly see the doublet that we talked about in the last slide. Compared to the smaller concentration, the fringes are not as distinct as the larger concentration, and also with the spectrum that is associated with it, it has a lower count, and some of the lines that we should see that are distinctive to sodium sulfate is not distinctive because it is not enough Raman signal to detect those.
So when we measured ammonium nitrate, we were able to observe three peaks that were noteworthy. We can see that comparing the 9 or 1046 inverse centimeter peak, that would correspond to a shift from 532 nanometers to 561 nanometers. So if you look at our middle plot, you can see that the largest peak, which corresponds to the 1046, is sitting at around 562, 563 nanometers. So this, though there is a slight difference, our calibration sees that our peaks line up at roughly the correct location. Now, if you look at the right side, sitting at around 590 nanometers, we believe that this might correspond to the 1500, 1600 inverse centimeter peak, as seen in the reference spectrum on the right. The intensity of this peak, we're not entirely sure why this one is larger per se than the doublet sitting in the middle, but it should be noted again that these gratings were tilted in order to recalibrate our system. So this might be partially why the intensity of these peak is larger, but for the most part, we believe that we at least have the positions of the wavelengths properly set. Now, comparing the intensity levels for different concentrations with ammonium nitrate, again, the exposure time is kept the same, and we have two separate concentration levels. All of them were prepared each with 1750 and 550 for each chemical. Now, it's not as immediately obvious as before in terms of at least the brightness of the fringes themselves. If you look at the top left image, the fringes, that's the 1750 milligram per milliliter fringes for ammonium nitrate, and compared to the bottom, they actually look, just based off of observation, they look pretty much the same. But when you look at the plot of the spectrum on the bottom right, you can see that there is a noticeable difference in intensity levels compared to the top spectrum. So though we have different concentration levels and the fringes look roughly the same in terms of intensity, we are seeing somewhat of an intensity drop from concentration level to the next.
So to make sure that our spectrometer was accurate, we used 10 measurements for potassium perchlorate. And so for this one, we use concentration level 2, which has the lower concentration of the two that we used. So as you can see on the left, we have a table exposure time versus intensity of a 562 nanometer peak. And you can see the numbers that are associated with it. And the average intensity is 106.912. And on the right, it has the graph that is associated with the table, just to give another visualization. So as you can see, around 1 millisecond, the laser in our spectrometer starts to saturate. And as you can see, we also put error bars to show another visualization of how accurate each distinct peak is. So since the error bars are kind of large, that means the points are more spread out and not as concrete as smaller ones. So to make sure that our spectrometer is accurate, we use 10 measurements for potassium chloride below level 1 concentration, and that is the higher concentration of the two. And as you can see again on the left side, we see a table of the exposure time versus intensity and a graph that is associated with it. And the average intensity is 111.9529. And on the graph on the right, since it shows large error bars again, that means the points that we used, or is shown below, are more spread out and not as concrete.
So we have two separate plots that illustrate the relationship between intensity versus increasing concentration level. We have two plots, one with an exposure time set to 10 seconds, and the other plot with an exposure time set to 5.2 seconds. Though we only have two concentrations prepared, we feel that these plots are still able to illustrate the relationship that as concentration increases, so does intensity. But of course, it would always be helpful to have more samples of concentrations set up. However, we did notice that for a certain exposure time, the intensity level saturates, and this can be illustrated in the previous slides. But at around 5 to 6.5 seconds, the intensity begins to saturate. And as you increase your exposure time, the intensity tends to drop and stabilize at a certain level. But overall, we can see through these plots that as the concentration level increases, we can see that the intensity increases as well. So jumping from 550 to 1750, we can see that the intensity increases.
For the senior design project, on the optical side, we had optical setbacks. Some of the problems that we ran into was our oxidase laser was weak to have fringes be detected at a good amount of time, so we found a new laser from Ocean Insight because it was strong enough. The next problem was gratings were not clean and had defects. So the solution is that we got new gratings from Thor Labs for the spectrometer for better results. The next problem was that the spectrometer was very sensitive and had to keep realigning, which led to poor resolution. And we spent hours on this because the slightest touch would just mess up the fringes. So we had put more collars and more stable mounts on the optical breadboard, and we put different bafflings to make sure that the light wouldn't come in. And then our next problem and our last problem was that the camera that was bought was too big and had like a big sensing area than the camera that we used before. So we used another camera that fixed that problem. On the optical side, we had design constraints and standards that we had to abide by. The biggest constraint was that the laser we were using for this project was a class 3B, so it would be very dangerous if you looked at it directly or got it laced into your skin. So we had to be very careful with that when aligning and testing sulfur. Another constraint was that the chemicals that we are using are flammable and can be harmful to the skin and eyes if it was not handled properly. So we used a fume hood and gloves and eye safety if needed.
This is the hardware block diagram. It shows all the hardware, the physical pieces of our system, and how everybody worked on them with color coding and how they relate to each other. So everything starts at the computer, which controls the XY table, which holds our samples. The computer also controls the laser, which goes through our spectrometer and then goes into the camera for image capturing to create the Raman graphs in the first place. And attached to the computer, we have the auxiliary components, the microcontroller, which gives our temperature and humidity readings for our measurements, and also the safety interlock to prevent people from going into the enclosure while the laser is in operation, along with a cooling fan to keep everything cold. The microcontroller is powered by a separate power supply that we also bought, and the computer and the laser also have their own, but since those are off-the-shelf components, we left them out of the diagram. Thank you.
Humidity and temperature are big factors in our system since they directly correlate with the performance and the accuracy of our spectrometer. Since we're dealing with water samples, ventilation and moisture are factors that are key to the correct functioning of our system and that we want to keep under control. The chip that we're using is the HIH6030, the left one on the picture. We chose this one because it has I2C communication and our MCU supports that. The way that we are doing this communication is by sending two requests. The first one is the first request for the chip to make a reading. The second one is to actually get the reading and the values into our microcontroller. And the way that we do this is by receiving the values, and then we have to go through conversion to convert the bits, since not all the bits that we receive are going to be useful, since some of them are just status bits. So we have to take off from the bits so that we can get the accurate reading from the humidity and the temperature, since they are sent at the same time, and we have to split the bytes and then cut off the bits and then send it through a whole formula so that we can get the actual temperature and humidity value. These values are then going to control the fan, and the requirement for the fan was to draw less than 500 milliamps for our power distribution to not have such a load. In this image slide, I'm showing the whole PCB layout for the whole circuit board, and we can see on the top side we have the PSU connector, we have the rails for the 3.3, the 12 volts that are powering the different peripherals that require them. We have 24 volts down here as well for the latch connector and the USB layout. And we'll be going more in depth on each of these in the following slides. Our PCB is done through Altium Designer. For many of the devices in it, we use the manufacturer recommendation. This was a big challenge at first that we wanted to go through because it is highly used in the industry, and we weren't familiar with it at the beginning. In the picture, we see the fan pins which control our fan. It is comprised of the diode and logic gates so that we can boost the current that we get from the signals in our microcontroller so that we can properly control the power going to the fan and turning it on and off. And this is also what we do with the latching device that we will see in the following slides. In this slide, we see an extended images of the schematics for our PCB. On the top left side, we see the schematic for the sensor, as well as the logic for the fan. And right below, it has the connector, which has the programming pins for the MCU. On the top right side, we see the logic for the latch control. And right below, we see the USB interface. We see the isolator as well as the USB to UART converter, the LEDs, and its connector, and as well as a device for protection of the signals. So a quick overview of the power distribution. As previously said, we are running off of 24 volts from our main power supply. It actually runs on 3 amps, as we see on the comparison table on the right side right here. We are using two buck converters. They are the same manufacturer part, but we have two of them for the two different rails. So we're using the 12 volts and the 3.3 volt rail. So the layout for this component was done using the manufacturer recommendation, which is to keep the current loop as tight as possible, as we see here, for dealing with the frequency and the whole reliability of the rail not being affected. And the reason that we went with this one instead of the other ones was for the simplicity of the Webench outputting this design for us. The microcontroller that we're using is the MSP430 FR6989. We are programming it through SPI-by-wire technology, which requires 4 pins, which is SBWTCK, SBWTDIO, ground, and 3.3, which we see on the picture on J3. We connect these 4 ports onto the launchpad that contains the interface that we need to program our device, and from there we can flash code from the Code Composer Studio into our microcontroller, and when it's done we can disconnect it and the code will continue running in our custom board for our needs. The reason that we got this device is because for the programming feature, as well as it has all the needs that we have, and it has many different ports as well as the protocols that we need, such as UART and I2C. The USB layout comprises one of the most complex parts within our system. The reason for this is that we are dealing with differential pairs, which require lots of trace specifications, as well as lots of little things, since we are dealing with high-speed signals, which are from the USB. So the reason that we need this interface is to connect the UART to USB for our PC coming from our microcontroller, and create the connection that we see into the GUI from the values in our board, so that we can properly manage them and handle the values that we get. We also have an isolation, since we have 5 volts coming in into this digital side, compared to the 3.3 volts that we have in the analog side for the microcontroller. This was one of the toughest parts to troubleshoot, since at first we weren't able to see something happening, and the reason for this is because we had to get the code right in the microcontroller before we could ever were able to see anything going to the PC. So we were in the limbo of not knowing if this was working, until we make sure that the code was working. So uh, when we finally did see something, is because of the LEDs. D2 is for transmission values, and D3 is for receiving values. So every time that we are either receiving or transmitting, the LED that corresponds to that will turn on and it will continue to flash as the code, based on the code.
So this is the safety interlock that we decided to use at the end of the day. It's an IDEC HS1L, and as you can see, we have an image with a bunch of them. The one on the right is the specific implementation with the actual key you can see going in. And what this does is basically using the electrical signaling from our PCB, we are able to control how the safety interlock is either closed or opened. That way it's locked or unlocked, and we can keep people out of the enclosure to prevent eye damage due to lasers. We had many options for safety interlocks. If you go on Mauser.com and look for them, you get thousands of results. I narrowed it down to these three mostly because of price concerns, and also I wanted one thing that worked with the 24-volt power supply that we have already. So what ended up happening is the main specification I chose it from ended up being the clamping force, just because I want to be able to hold the enclosure closed as much as possible. And if you really put your weight into it, you might be able to cross the 1200 and 1500 Newton forces, but I don't think 3000 is that possible for people. It also happened to be the cheapest, so it was the clear-cut choice by the end of it. This is the XY table, and it allows us to hold multiple samples at once instead of having to scan samples one by one. It holds the well plate with multiple wells, and it's controlled by a controller that we bought along with it. And yeah, it just moves our samples around and allows us to have many more samples without having to change your sample holder for multiple scans in a row. So these were the options for XY tables that we were looking at originally. One thing that really was very obvious was that they happen to be very expensive. So price was not really a consideration given that they were all costly. And ultimately we decided on the Zaber ASR one because XY tables usually need to come with a controller that is also expensive, but the Zaber model, the Zaber ASR, came with a microcontroller that automatically detects it, which made our lives much, much easier in regards to programming and controlling the XY table.
In order to be able to operate the spectrometer, the computer you utilize must be capable of installing and running MATLAB, as well as all the supporting libraries that allow communication between the software and the various hardware components that make up our system. The team explored 3 different computer options that were readily available, and after some deliberation, we decided to go with the highlighted ZenBook. The reason we chose this computer is because it had the largest storage capacity to hold all the pictures and data collected by the spectrometer, the most amount of RAM available to complete these calculations, and the speed increase of the SSD HDD hybrid was an added bonus. So on the left, you can see an image of our GUI. The point of the GUI is to essentially control everything that is capable of being controlled through software. So on the bottom left, you can see initialize and it says motor and temp sensors. So here you have a drop-down um, lists that show different COM ports. Each computer is going to have its own COM ports for each of these, depending on how it's all wired up and plugged in through USB. So to determine which COM ports you have to go into a device manager to select the right one, hit initialize. Once you've hit initialize on the motor, the not connected will change to connected, and you'll be able to then go over the motor setup, hit go to start, change the number of microsteps it takes, so on and so forth. The same applies to the temp sensors, temperature and humidity sensors, um, but instead of having its own setup panel, it's just pulling the sensors. So when you hit that pull sensor button, the temperature and humidity displays underneath it will be updated. Um, Also, for of the majority of the buttons, when you hit user or when you do an operation, the user info box will be updated as well. Um, that was omitted in the demo, but it is currently in place. As for the spectrometer setup, the spectrometer isn't controlled through serial commands. So it's essentially just always plugged in and ready to go with the camera as long as there's power to it. So the code will, when you hit the capture image, um, assuming that the laser is on, the detector is detecting some kind of um, signal. And so what the detector will do when you hit that capture image is take that image and then allow you display it on your screen, and it'll allow you to save it to a specific folder that you want. Once you have that image saved, you can hit get spectrum, go back to that image that you just took, select it, and once you hit open, the graph will update at the bottom here, and it'll say um, intensity or uh, some kind of Raman spectroscopy will appear there. For a different spectrometer, you can also use adjust the integration time to so all you would do is type in the value that you would like in seconds underneath the integration time and hit set, and that would be it. As for the laser setup, the turn emission on and off is also for a different laser that might be implemented at a later date. But in the meantime, the edit laser will run an executable that would directly control the laser. Um, this is due to some proprietary software, and this was the best that the company that we got the laser from could provide for us. Finally, we have the lock and unlock. The reason I put this in the laser is because it's mostly a feature to prevent people from looking over the top of the laser when it's on. So there's a latch at the top of our system that when you hit lock, if you hit lock, it will not be able to open up. And when you hit unlock, it is able to open up. The reason for this is normally whenever you're running the laser, you would hit lock and you wouldn't be able to open up the little latch and get the laser shine directly in your eyes. So this is the software block diagram. It demonstrates how the software works with the various hardware components in our system. The first thing you're gonna do is run the MATLAB program. Once this is done, you'll see the GUI that I showed a few slides ago. And what you're gonna do is you are going to then select the ports that the hardware components are connected to. You can determine which ports those are by going into device manager. Once those are correctly selected, you're able to initialize. Once those are initialized, they'll be connected, and you will see message appear in the message box on the top left that say whether each component is ready. Once the motor and laser are ready, you'll be able to initialize the spectrometer, and at that point, all three components are ready, and you can begin to run the spectrometer itself. The first thing you're going to want to do when running spectrometer is positioning the well plate over the laser. Um, you're going to want to position the well plate so that the sample itself is over the laser because that's what the laser will be going through. Um, Once you've turned on the laser, the spectrometer will run, the camera will start taking pictures, and after a while, the spectrum itself will be collected. You can then turn off the laser. The software will perform the Fourier transformations and other calculations to get the actual graph that means something to people. Once you have this, you can export it, clear the spectrum, position the well plate over the next sample you wish to analyze, and this process starts again. So Fourier transformations are actually vital to being able to generate the waveform that means something, the spectrometer results. So what happens when you run the lasers is that a camera takes pictures of the light that comes out through the sample. This camera is called the IDSI, and it is what actually converts these images into mathematical matrices. You can see an example of one of those images on the top left. They don't look like much, but after a series of conversions and calculations and eventually a Fourier transform, um, the numerical matrices are transformed into a graph. The graph is what you see at the bottom left, and it has peaks at certain wavelengths, and each of these wavelengths corresponds to a specific chemical makeup um, or chemical signature, and this these combined signatures will tell you what exactly is present in the sample being analyzed.
So this is our budget, and the majority of the money went towards our XY table with the motor controller that comes with it. There are precision tools used for microscopes, so we expected these to be expensive to begin with. And Ocean Insight, our sponsor, also told us about this, and we were well aware of that going in. And overall, we were actually able to stay slightly under budget, which is amazing. And here are all the piece by piece breakdowns for you guys to see. Thank you.